we will discuss the concept of probability measures and their fundamental properties. A function that takes a set A as its independent variable to compute a value, such as p of A, is called a set function. Probability is a set function p that assigns a numerical value p of A to each event A in the sample space S. This value is called the probability of event A. The rigorous definition of a probability measure will be presented on the next page. Let S be a sample space with an associated sigma field F. A probability measure P is a set function defined on the sigma field F with range the closed interval from 0 to 1, satisfying three conditions. The first condition says that the set function P is non-negative. The second condition says that the probability of the entire sample space S is equal to 1. The third condition says that the set function P must satisfy sigma additivity. Here, sigma denotes countable infinity, while additivity applies to pairwise disjoint events. That is, given a sequence of countably pairwise disjoint events A sub 1, A sub 2, A sub 3, all the way to infinity, the probability of the union of all these events is equal to the sum of their individual probabilities, as shown in the last line of the mathematical equation. The definition of the probability measure P on the previous slide represents an axiomatic approach to describing probability. We often use this kind of axiomatic framework to build theoretical mathematical models, which allows us to perform logical reasoning using mathematical tools. Using the previously established axiomatic conditions, we can prove that the probability of event A occurring is equal to 1 minus the probability of event A not occurring. The first line shows that the entire sample space S can be written as the union of event A occurring and event A not occurring. The non-occurrence of event A can be conceptualized as the complement of A. Therefore, set A and its complement A complement are mutually exclusive events. Consequently, by applying the axiomatic conditions of the probability measure, we obtain the mathematical formula in the second to last line. Here, the first equality follows from the second condition, while the final equality utilizes the third condition, as set A and its complement A complement are mutually exclusive events. This completes the proof. This experiment consists of flipping a fair coin successively until the same face is observed on 2 consecutive flips. Let A equals 3, 4, 5, and so on to infinity. Then, set A represents the event that it will take 3 or more flips of the coin to observe the same face on consecutive flips. We aim to calculate the probability of event A described on the previous page. Here, we will utilize the property that the probability of event A occurring equals 1 minus the probability of event A not occurring. This approach is taken because calculating the probability of the non-occurrence of event A, which is its complement A complement, is much easier. The non-occurrence of event A corresponds to the experiment terminating after just 2 flips, meaning that 2 consecutive flips yield either 2 heads, HH, or 2 tails, TT. All possible outcomes for 2 flips are shown in the third line, totaling 4 outcomes. Consequently, the probability of event A not occurring is presented in the third to last line. Applying the aforementioned property, the probability of event A occurring is 1 minus the probability of its non-occurrence, yielding the final result shown in the last line. Using the previously established axiomatic conditions, we can prove that the probability of the empty set event is 0. Assuming event A is the empty set, the complement of A is the entire sample space S, as shown in the second line. According to the property established earlier, the probability of event A occurring is equal to 1 minus the probability of event A not occurring, which yields the calculation in the second to last line. This completes the proof. This screen illustrates 2 intuitive properties. The first intuitive property states that a larger event set corresponds to a higher probability. The second intuitive property indicates that the probability of any event cannot exceed 1. Their proofs are presented on the next page. First, we prove the first property. Since set A is contained in set B, event B can be decomposed into two mutually exclusive events, as shown in the second line. That is, set B can be written as the union of set A and B intersect a complement. Furthermore, these two decomposed sets share no common elements and are therefore disjoint. Consequently, by the third condition of the probability measure, the probability of event B equals the sum of the individual probabilities of these two mutually exclusive events, as presented in the second to last line. Applying the first condition of the probability measure, that is, the probability of any event is non-negative, yields the result shown in the final line. This completes the proof of the first property. Next, we prove the second property. Since any event A is contained within the entire sample space S, it follows from the first property that the probability of event A is less than or equal to the probability of event S. By the second condition of the probability measure, the probability of event S is equal to 1. This completes the proof. Using the previously established axiomatic conditions, we will prove the formula for computing the probability of the union of two events. Because the union of event A and event B can be decomposed into two mutually exclusive events, as shown in the second line. That is, a union B can be written as a union B intersect a complement. Furthermore, these two decomposed sets share no common elements, meaning they are mutually exclusive events. Therefore, by the third condition of the probability measure, the probability of a union B equals the sum of the individual probabilities of these two mutually exclusive events, as presented in the final line. Next, event B can also be decomposed into two mutually exclusive events, as shown in the second line. That is, set B can be written as the union of A intersect B and B intersect a complement. Furthermore, these two decomposed sets share no common elements and are therefore disjoint. Consequently, by the third condition of the probability measure, the probability of event B equals the sum of the individual probabilities of these two mutually exclusive events, as presented in the final line. By rearranging the terms in the last equation on the previous screen, we obtain the second line shown on the screen. Since the equation on the second to last line was proved previously, combining these two expressions completes the proof. A faculty leader meets two students in Paris, one arriving on a train from Amsterdam and the other on a train from Brussels, with both trains scheduled to arrive at approximately the same time. Let A and B denote the events that these two trains arrive on time, respectively. Based on past experience, the probabilities of event A, event B, and both events occurring simultaneously are shown in the second line. Therefore, using the property proved earlier, we can compute the probability that either event A or event B occurs, as presented in the second to last line. This value represents the probability that at least one of the two trains arrives on time. Using the previously established axiomatic conditions, we will prove the formula for computing the probability of the union of three events. First, we view the union of three events as the union of two events, as shown in the first line. By treating B union C as a single event, we can apply the probability formula for the union of two events, as presented in the second line. Furthermore, for the probability of B union C in the second line, we can apply the two-event union formula once more to obtain the expression in the second to last line. Next, we need to compute the last expression from the previous screen. We observe that this expression also represents the probability of the union of two events. Therefore, applying the formula for the union of two events once more yields the equality in the second line. Combining this equality with the one from the previous screen completes the proof. Continuing from the previous example, suppose a third student arrives on a train from Cologne, and let C denote the event that this train arrives on time. Based on past experience, the probabilities associated with these related events are shown in the final line. Using the previously derived formula for the union of three events, we can compute the probability that event A, event B, or event C occurs, as presented in the second line. This value represents the probability that at least one of the three trains arrives on time. This theorem presents the formula for computing the probability of the union of n events. It can be proved by mathematical induction together with the formula for the union of two events. Suppose that we have a sequence of events a sub 1, a sub 2, a sub 3, and so on to infinity. We say that this sequence of events is increasing, which means that the sets become progressively larger, as shown in the second line. Similarly, we say that this sequence of events is decreasing, meaning that the sets become progressively smaller, as shown in the second to last line. When a sequence of events is increasing, we define its limit as the union of all the events, as shown in the third line. Intuitively, this represents the final term of the sequence, that is, the infinite th term. Similarly, when a sequence of events is decreasing, we define its limit as the intersection of all the events, as shown in the last line. Intuitively, this likewise refers to the final term of the sequence, namely the infinite th term. This theorem states that when a sequence of events is either increasing or decreasing, the probability of the event at infinity equals the limit of the probabilities of the individual events. On the last line, the left-hand side of the equality represents the probability of the event at infinity, while the right-hand side is the limit of the individual probabilities, that is, the limit of a sequence of real numbers, where the nth real number is the probability of event A sub n.